speaker of today's session is Konstantin Vorob'ev from Sobolev Institute of Mathematics. So the floor is yours, please.
Okay, thank you. It's always a pleasure for me to participate in this work. So I will talk about equitable two partitions of the Johnson graph. This is a joint work with Rhys Evans, Alexander Gavrilyuk, and Sergei Goryainov. Okay, so let me start with the outline. So I will start with definitions, with discussing previous results. Also, I provide some examples. Then I will present our main result and two methods that we use to prove the main theorem. So the first one is based on local structure of partitions, and the second one is based on so-called partial differences in Johnson graphs. And I will finish with some discussion on further directions. Okay, so what is a Johnson graph? So we have an n-element set. So the Johnson graph J of nW, for where n is at least 2w, is a graph with the set of vertices with all w subsets of the n set. And we say that two vertices x and y are adjacent if the intersection of x and y is equal to, if the size of the intersection is equal to w minus 1. So it's easy to see that it's possible to define a distance in this graph, which is equal to the, so the distance from x to y is equal to w minus the size of its intersection. So actually, in terms of coding theory, vertices of the graph can be treated as binary vectors of length n, containing exactly w1s, and two vectors are adjacent if two vertices are adjacent if corresponding vectors differ in exactly 2 coordinates or have having distance 2. So here are some simple examples. So J of n1 is just a complete graph K sub n, and J of n2 is just the line graph of K sub n. Okay, so what is known about the Johnson graph? It is a distance regular graph of diameter w, and it has w plus 1 distinct eigenvalues, which are given by the following formula. So lambda sub I of nw is equal to w minus I multiplied by n minus w minus I for all I from 0 to w. So corresponding eigenspaces have dimensions n choose I minus n choose I minus 1. And we have the following equation for every eigenvector from Vi. Here M is the adjacency matrix of the Johnson graph. Okay, so as for the Johnson graph J of n3, so there are exactly 4 different eigenvalues from 0, 1 to 0, 3, and 0, 1 is just the degree of our graph because it's regular, so it's equal to 3 multiplied by n minus 3. Next, so we have defined eigenspaces, but for our purposes, it's more convenient to use the language of functions instead of vectors. So let me define the lambda eigenfunctions of a graph. So if you have a graph, we have a real valued function defined on the vertices of the graph. And so this function is called lambda eigenfunction if the equality, the following equality holds. From the left side, we have lambda multiplied by f of x, and from the right side, we have the sum of values of f over all neighbors of x in the graph. So actually, it is the same as the eigenvector, but in the language of functions. Okay, so the next notion we need is the equitable partition. So I think you all know it, but let me remind it. So we have an R partition pi x1, x2, and xr of the vertex set of some graph, and this partition is equitable with the quotient matrix S with size r by r if every vertex from x sub I has exactly Sij neighbors in xj from xj, and these sets are called cells of the partition. So this the equitable partition is also known as a perfect coloring, regular partition, partition design, and also an intriguing set in case of two cells. So here you see an example. So we took a 3x3 grid, and this equitable partition, pink, yellow, and blue. And we have matrix, 3x3 matrix with corresponding parameters. So there is a popular result that eigenvalues of the quotient matrix of a partition must be eigenvalues of the adjacency matrix of a graph. For example, it can be found in the book by Tsvetkovich, Dup, and Zaks. So by an eigenvalue of partition, we will understand an eigenvalue of its quotient matrix. Okay, so now about main motivation of this theme. So there is a famous conjecture by Descartes from 1973 that there are no non-trivial perfect codes in Johnson graphs. Actually, Sergey in his previous talk has given a definition of a perfect code, but let me remind it. So a perfect, an R perfect code is such a subset of vertices of the graph that if we take balls of radius r with centers in these vertices, then we will cover the whole vertex set of the graph without intersection. And if we consider one perfect codes, so the balls of radius r, then it is exactly an example of equitable two-partition, for example, in a Johnson graph. So this conjecture is still open, especially for the case of one perfect codes. In particular, so there are a lot of papers by Banai, Rus, Edson, Schwartz, and others. And so the most recent strong results may be found in the papers by Edson. And so as for the one perfect codes, Gordon in 2026 showed that there are no trivial perfect codes in Johnson graph J of NW for n up to 2 to the power 250. Okay. Yes, so the idea is that if we prove some interesting theorems for equitable two partitions, then we can somehow use it for this conjecture. Okay, so what do we know about equitable two partition in Johnson graphs? So here you can see some simple properties. So let M be the quotient matrix with the entries A, B, C, and D. Then since our graph is regular, we have A plus B is equal to C plus D is equal to the degree of a graph. Then we know the spectral of the graph. It is the degree of the graph and the value A minus C. Also, it's easy to compute the sizes of cells of our partition. And for our purposes, without loss of generality, we took B is not greater than C. So in these terms, let us formulate the main problem. So first of all, let us define the equivalence for function defined on vertices of Johnson graph. So if you have two functions, real valued, defined on the vertices of the Johnson graph, so they are equivalent if there exists some permutation of coordinate positions such that they are equal after the usage of this permutation. And we say that two equitable two partition C1, C2 and C1 prime, C2 prime of the Johnson graph are equivalent if the characteristic function, say of C1 is equivalent to characteristic function of C1 prime or C2 prime. And the main problem can be formulated as follows. So if we have some quotient matrix, so the question is there an equitable two partition of the Johnson graph with this matrix M? And if yes, then what is the number of non-equivalent partition with this matrix, or the number of different partitions with this quotient matrix? So let us consider an example. So here we have a Johnson graph J of 6, 3. So as you remember, it's all the vertices of the graph are all vectors of length 6 with exactly 3 ones. So let us take a vertex and consider its neighborhood. So you see that the neighborhood is a 3 by 3 grid. And now let us consider the antipodal vertex. Okay, so now we have 20 vertices. It is exactly the vertex set of our graph. It is of degree 9. So now we need to draw some more edges. So we took one more pair of vertices, which is antipodal, so they are not connected. And we draw edges in the following way. So we just connect yellow with red ones. And after drawing all the edges, we have the following picture. So what is known about equitable two partitions of this graph? So all these partitions were listed by Augustinovic and Mogilnych in 2008. And so they show that such partitions must have one of the following quotient matrices. So here you see the list, 7 matrices. And so the easiest one is a pair of antipodal vertices, so a pair of vertices at Hamming distance 6. And you see that the quotient matrix, this quotient matrix 0, 9, 1, and 8 actually is the quotient matrix of a perfect chord. So this is exactly an example of a trivial one perfect chord. So if we take balls with centers in these vertices, balls of radius 1, then we will cover all the graph. Okay, that was an example. Yes, and if we take two pairs of, for example, two pairs of antipodal vertices, then we have the quotient matrix 1, 8 to 7, and so on. Okay, so let me remind you what we know about equitable two partitions. Now we will consider only equitable two partitions with the eigenvalue lambda 2. So I will explain why a little bit later. So we have a partition x1 and x2, the quotient matrix p sub 1, 1, p12, p21, and p22. So without loss of generality, p12 is less than p21. Well, it's also possible that they are equal, but this case is not interesting for us. Also, we know the sum of rows, it is equal to the degree of a graph. And one more equation is p12 plus p21 is equal to 2n minus 2. This is from the fact that lambda 2 is an eigenvalue of our matrix. Okay, so this is what we know. And some historical part. So equitable two partitions of the Johnson graph J of n and w, so they were characterized in the following cases. So if this partition has eigenvalue lambda 1, then it was made by Meyerowitz, and actually such partitions have quite simple structure. Then if equitable to partition, but for W equals 3, and with the eigenvalue lambda 3 of n3, so every such partition corresponds to n3 lambda design. So in some sense, this problem is solved because all such parameters n and lambda are known for when such designs exist. But of course, the problem of finding all non-equivalent designs, I'm not sure that it can be solved any day. And the last case, when W is at least 4 and the eigenvalue lambda 2 is the eigenvalue of our quotient matrix. So such partitions were characterized by me in 2020. It's still a preprint, but I hope it will be published soon. Okay, and also partitions of Johnson graphs J and 3 were studied by Augustinovich Mogilnych in a series of papers. In particular, in 2008, they listed all admissible quotient matrices for graphs J63, 73, and in 2011 for J83. So as we see from this information, for a Johnson graph J of n3, the only remaining case when the eigenvalue lambda 2 is the eigenvalue of the quotient matrix. And here you see the theorem by Gavriluk and Goryainov from 2013. So they showed that there are no equitable partition of Johnson graphs J and 3 with the second eigenvalue, but only for odd n. Also in that paper, they classified all partitions for even n, but only for symmetric quotient matrices. So here, it means that the only open case here is when n is even and the quotient matrix is not symmetric. So what is known here? There are 3 known infinite series of equitable two partitions of Johnson graph J to M3, so to M it's even case, with the second eigenvalue. So here you see 3 matrices. The first and the second were found by Gottsel and Prager in 1997, and the last one by Augustinovich and Mogilnych in 2011. So if we look at these matrices, it may seem that they are completely different, but in some sense they are connected. So let us consider the following construction. So here we have a so-called cocktail party graph. So it is a complete bipartite graph with parts of size m. And after that, we delete one perfect matching. So this is the graph. And it's easy to understand that there are exactly 3 types of unordered triples of vertices in this graph. So the first type is if we have 3 vertices in one part or in another. The second type, if we have 2 vertices in one part, one in another, and 2 vertices, so they are from that perfect matching. And the last case, if we have two in one part, one in another, and they are not in that perfect matching. So actually, if we consider this partition into 3 sets, it's easy to show that this partition is equitable. And here you see the quotient matrix of this partition. So it is a 3 partition, but let us look at this matrix. For example, at the last column. So in the last column, we have 2 values that are equal to each other, namely 3m minus 6. It means that if we merge the second and the first and the second cells into one, so it means then we will have again a partition, and it it will be again an equitable two partition. And the same procedure can be done for remaining two pairs, for the first and the third, and the second and the third cells. So after this merging, we have three equitable two partitions, pi1, pi2, and pi3, with corresponding quotient matrices. So actually, this is exactly the matrices we have discussed before. Yes, so, and here M is a parameter, so this is three infinite series of equitable two partitions. And our main result here is the following. So if we have an equitable two partition with the eigenvalue lambda 2 and n is at least 12, the Johnson graph is J of n3, then the partition X can be constructed from a matching on the elements of the set of n set, which corresponds to an instance of a partition pi1, pi2, pi3. In other words, it means that every such a partition must be equivalent to a partition pi1, pi2, or pi3. Actually, so we see 4 authors here, and this result was proven by 2 different approaches. And now I will talk about these approaches. So the first method is based on so-called local structure of equitable two partitions. So let us define for a vertex of a graph, an xy indicator is such a function that is equal to 1 if the vertex is an element of x1, 0 otherwise. And in the same manner, we for a subset of vertices, we also define this u overlined as a sum of corresponding functions. It is known that the neighborhood of any vertex of a Johnson graph is isomorphic to the 3 by n minus 3 lattice. In particular, there are 3 maximal cliques of size n minus 3 in the neighborhood of ABC, and we will denote them as AB star, AC star, and BC star. And also n minus 3 maximal cliques of size 3 of the following form. And also, let us denote by AB row the set AB star minus this vertex ABC. So this is some technical stuff. Okay, so and main lemma here is the following. So if we have a vertex of a Johnson graph J and 3, this is an element of the first cell, then we have the following equation. So from the left side, we have the difference of 2 overlined cliques. Yes, and from the right side, we have a sum of some values multiplied by n minus 4 divided by 2. So we know that the size of this ij star overlined is at most n minus 2. So the difference, this difference is equal to h n minus 4 divided by 2 for some h from minus 2 to 2. Now, without loss of generality, we fix a vertex ABC in our graph such that AB star overlined is greater or equal to AC star overlined, which is greater or equal to BC star overlined. And then we define the difference tuple of this vertex ABC, which is the pair AB star overlined minus AC star overlined and AC star overlined minus BC star overlined. And as a result, we have 6 possible variants of these different tuples. So you see cases from 1 to 6. And each case requires some time and space to prove. So actually, the whole proof for all cases is more than 10 pages. And here you see that cases 5 and 6 are red. And it means that only these cases lead to some existing two partitions. So cases from 1 to 4, they lead to so they do not in these cases no equitable two partition exists. Okay, so let us consider so-called NB array. So again, we have a vertex of a partition, which is a lambda 2 equitable two partition. Then we consider the neighborhood of our vertex ABC, and at each vertex, so the corresponding entry of each vertex in this neighborhood is equal to this vertex overlined. So it means that we have a 3 by 2m-3 array, which consists of zeros and ones. And the idea of the case analysis is to take some case, for example, case 2, and to find all possible NB arrays that can exist in this case, and just to check all the cases. So, for example, for the case 5, we have proved the following lemma. So ABC is the vertex of the Johnson graph Jn3, and ABC is an element of X1, and we have a difference tuple 0 n-4 divided by 2. So then there are only two possible NB arrays up to reordering for this case. Yes, so after all cases, we have proved the main result again. But what is important that this method works for n at least 15. And so let me talk about the second method, which is in some sense similar, and it is based on partial differences. So again, we see a definition of lambda eigenfunction of our graph. So we know it. And the idea is to consider the following difference. So if we have some function, real valued, on vertices of a Johnson graph, so we take two coordinates or two elements from our n set and define the partial difference FAB as follows. So for every W-1 subset Y, we took FAB of Y is equal to the difference, the following difference. So the idea that we have some function in the Johnson graph J and W, and after this procedure, we have a function defined on vertices of a smaller Johnson graph, J of n-2, W-1. And here we use one very useful lemma from Могильных Валеженич Vorob'ev from 2018. So actually, if we have a lambda I eigenfunction of a Johnson graph, and we take a partial difference, then as a result, we have the all-zero function or lambda I minus 1 n-2 W-1 eigenfunction of a smaller Johnson graph. So the idea is to take our partition, consider a characteristic function of one cell of this partition, and just take a partial difference of this characteristic function. So an alternative way is to consider a partial difference of the following function f, where f is a lambda 2 eigenfunction of a Johnson graph, and it is so it depends on elements of the quotient matrix. Yes, and the idea is that the result, the partial difference, is a lambda 1 eigenfunction of a Johnson graph J and 2, and it takes only three distinct values, -1, 0, and 1. So it means that the problem of constructing equitable two partitions may be reduced to the problem of constructing lambda 1 n-2 W-1 eigenfunctions of a smaller Johnson graph with some restrictions. So the main lemma here is the following. So let f be lambda 1 and 2 eigenfunction of j and 2, taking values -1, 0, and 1. F is not identical to 0 function, n is at least 5, then f is equal to one of the following functions, well, up to multiplication to -1. So here we have functions of two types. In the first type, we see that the function defines only on elements n and b. So we will say that a and b are defining elements of f1. And in the second case, f of f2 of x, it depends on sets m1 and m1 and m2 are defining sets of the function of the second type. Yes, and one more useful lemma. So if we have a, so now we know that our partial differences can be of two types, and also the third opportunity is when it is the all zero function. So if we have a lambda 2 equitable to partition of a Johnson graph, n is at least 7, we have a quotient matrix, we take a characteristic function of one cell, and we consider the set of all possible partial differences of our function g. So suppose it has T1 and T2 partial differences of types 1 and 2 correspondingly, and the rest of them are the all zero differences, then we have the following equation. So some numerical condition. Yes, and here we also have some case analysis. So let me show it by example. So for example, we start with the characteristic function g of x1 of our partition. So suppose that there are no partial differences of type 1, then only of type 2 and all zero functions. So we take some not identical 0 f1, 2 with defining sets m1 and m2. And so by definition and structure of this function f1, 2, we know that these vertices are element of x1 and x2. Then we consider different partial differences for other coordinates, and step by step we construct our partition. So as a result, we show that the only possible case is the partition by 1. Well, it works for n starting from 12. And in the second case, there is at least one partial difference of type 1. So we start with this, and also by some case consideration, step by step, we reconstruct the whole partitions. And in this case, we have partitions pi 2 and pi 3. Of course, it also requires some time. So the whole proof for these cases is about 8 pages. Yes. Okay. So as a conclusion, so this is our main result for equitable two partitions with the eigenvalue lambda 2 of Johnson graph J of n3 for n starting from 12. So actually, every such partition can be constructed from a matching on the elements of n set, which corresponds to an instance of a partition pi 1, pi 2, or pi 3. And as a question for the future, it's interesting. So is it possible somehow to generalize this method, so to find some new for lambda I equitable to partitions of the Johnson graph for I greater than 2. So we see that I equals 1 was made by Meyerowitz. So I equals 2 is also solved by different papers, in different papers. So the next step is I equals 3, and it is the question. Thank you for your attention.
Well, thank you, Konstantin. Thank you very much. Are there any questions to Konstantin? Well, it is a fundamental result, right?
Yes, in some sense.
Yeah, exactly. So you mean this open question, you mean that you are trying to apply, you are trying to understand, is it possible to use all the methods you have considered in the paper in general, right? Yeah.
In general, yes, yes. So if we use them directly, then the number of possible cases is just huge. Yes.
Right. Yeah. Well, but what is the way to reduce these cases?
So this is the question we should think
These are the
on.
questions.
Yes.
Group theoretical methods.
Perhaps.
I see. I see. Any further questions? Well, if not, then let us thank again Konstantin. Thank you very much. And since it was the last talk of our today session, so let me thank all our speakers giving talks today. It was wonderful to hear all these new results and just to understand that there are some open questions, and so we are looking forward very much to see and to know these new ideas and new results. Well, okay, thank you very much for all of you. And tomorrow we have also 4 talks. These talks will be more close to group theoretical approach, but still on graphs. So yeah, you are welcome to participate tomorrow. Thank you very much. See you tomorrow.